Hi, in this new video, we'll discuss how we are going to use the linear programming approach to solve the information design problem, but here we'll introduce a more complicated or a more general problem, and which is provided from the by the paper of Bergemann and Morris from 2019. So with multiple receivers or multiple decision makers, and let's see how we're going to solve this multiple decision makers information design problem with the linear programming approach. Okay, so let's do that. Okay, information design using the linear programming for multiple decision makers problem. Okay, so this example is taken from the paper we mentioned previously, Bergemann and Morris, 2019. Okay, so this game is called, in our paper, is called the investment game. Okay, so in the setting, there are two person. So there are two people there trying to invest in the market. Okay, so those two people, they are both the decision makers. Okay, and there is one information designer outside of this game. So namely, our I includes 1 and 2, and two agents, they have the same actions, either not invest or invest. Okay, and the state can be bad or good. Okay, so the market can be a bad market or a good market. So the prior for both is 1/2. Okay, so if the market now is bad, then the payoffs for the, okay, so this is the payoff. For the two players are as follows. So the actions can be not invest or invest. So if both of them, they do not invest, then they get 0/0, of course. If one invests, the other one doesn't, then the person who invests have some loss of -1, and the person who doesn't invest remains 0. Okay, and this is symmetric. If both do not invest, then they get -1, and in addition, we just add a very small number, okay, to this to indicate the additional effect from their investment from both people, okay, from both agents. So this epsilon could be positive or negative, so it reflects the substitution or the complementary effects of the two actions together. Okay, so later this epsilon will be pretty important when we solve our game using the linear programming. So, and it has some intuitions there. So this, if the state is G, okay, similarly write this table. So this is 0/0, okay, and for the person who invests, then they get X, and the other one gets 0. This is symmetric, and altogether, if they both invest, then both gets X, and of course plus this epsilon for the additional effect together. And of course, we assume X is a number between 0 and 1 strictly. Okay, and we also have some assumption for this epsilon, which is a very small number, pretty close to 0, but it's there. Okay, it could be positive or negative, and for now we don't have any additional assumption for that. Okay, so the reason why I assume that X is less than 1 is because that this reflects the fact that if there's no information, then people do not need to invest at all, right? So it has to be less than one more intuitively. Okay, so now let's further look at this problem and try to formulate that into our linear programming language. So before that, so normally we first try to understand to see what is the utility for the information designer. Okay, so this is the above is the payoff for the receivers, for the agents. So the designers payoff. Okay, so to the designer, from the perspective of this information designer, so they simply wishes to have people having investments. Okay, so it doesn't matter for this designer that either the agents they're benefiting from investment or they're losing money. So it doesn't matter for this designer. So the designer simply wishes to have more people's investment in the market. Okay, so that's sort of the like the misalignment of the interest between the information designer and the receivers, right? So that's pretty interesting and to further think about. Okay, so the big V for the designer payoff, if II and for any omega, so this could be 2, okay? And if I and any omega, and this is symmetric to the other case, the other way around. This is 1, if just one person invests. And if no person invests, and I for any omega, this is 0, okay? So this is sort of like the prosecutor. Doesn't care about the omega, but only cares about the actions, actually. Okay, so, and this sort of the setting is not always like this. Okay, so this is just one specific example for all those omega in either B or G. Okay, so before we formulate our linear programming problem, do we need to define those, or we just define some notations for the simplicity of the outcomes? So outcome, so this small v is outcome. Outcome V is a joint distribution over the state and action. So we use some notations to define those V's. So such as the V, okay, too many brackets, I, G. So we just use V, 2G to denote that. This is because that 2 people are investing here. We use the number 2 to simply denote those 2 people are investing here. Okay, and G is the state here. Okay, so that's a pretty straightforward notation and helps us to further simplify the problem. So the V, I, B, so namely this is V2B. So VI, NI, G is V1G. VI, NI, B is V1B. Okay. Okay, and we have another V1G, which is V of NII, so which is just symmetric to the previous one, to the to this one, right? Okay, and I this should be G. Okay, V1G and I B is V1B. Okay, we have this one also previously, and later at last we have NI G or B. So for G is V0G, VNI B is V0B. So we have those little notations for us to to help us to further simplify the notations later for the linear programming. Okay, so we have 8 notations here because we have 2 for the state, 2 for the actions, and two for each of those 2 actions of those 2 players, right? So we have 8 combinations. Okay. And here we notice that this and this are essentially the same, and this are essentially the same. So we have a pretty implicit remark is that those are symmetric, right? So we can use the same notations for the omega, all the omegas. Okay, so we have those 2 using the same notation, and those 2 are using the same notation. Okay, good. So that's how we simplify our notations for those outcomes. Then we are good to go to start the linear programming problem, actually, to formulate that one. So our linear programming is the maximization and by choosing the V's. So what are the V's here? Okay. So here the utilities, okay. If we just multiply those V's by the payoffs, right? By the designer's payoffs. And what we get is 2 V2G plus 2 V2B plus 2 V1G plus V1B. Okay. So the first constraint is the consistency, right? So it's the summation over A VA omega is mu naught. Okay, we're pretty familiar with that. And how about right? So that's the formula, right? So we need to actually to specifically write those down because we're solving some problem. So for the state is G, so namely it's nothing but V2G plus V1G plus V1G plus V0G. Okay, so this has to be the prior 1/2. So those V's we just get from those previous definitions of those things. For the states B, so correspondingly V2B plus V1B plus V1B plus V0B. So all those states has to be here, right? Okay, so this is also 1/2. So that's the consistency requirement. And how about the requirement for the obedience? So let's just write some note consistency for the BCE. And here we have the obedience. Okay. So for the obedience, so let's first say that we're looking at the action with I, okay, for the i's. So it's nothing but the expected for that is x plus epsilon, okay. So you can refer to those payoffs from here, right? So it's x plus epsilon times v2g and plus minus 1 plus epsilon v2b, okay, plus x v1g plus minus 1 v1b. And this is just a positive number, and this 0 is from the deviation, okay. Okay, so if deviation, then because this game is pretty simple, that we if there's no investment, then for this player, then this utility is 0. Okay, so nothing, no return or no loss from that. Okay, so that's for the I. So for the NI, okay, if the action recommendation is NI, then the obedience gets 0, right? Not investing. But if there's deviation, on the right hand side, if there's deviation, then this becomes x plus epsilon v1g plus minus 1 plus epsilon v1b and plus x v0g plus minus 1 v0b. Okay, so that's the second obedience part requirement for the recommendation of not investing. And in addition, we have all those outcomes to be positive, to be non-negative numbers, right? 0g, so which is similar to the previous example we already showed in the earlier videos. Okay, we have those 6 positive or 6 non-negative numbers. Okay, so before we simplify this problem, so let's just put this 0 to the other side, okay, and make this so this if we wish to change the direction of this inequality, then we just multiply by a -1 in front of it. Okay, so that brings some convenience for us to later solve this problem. Okay, this is smaller than or equal to 0, and we just multiply by a -1, and this is greater than or equal to 0. Okay, so that's pretty convenient for us to later solve the problem. And this is 1, this is 2. Okay, so we use 1 minus 2, okay, for their left hand sides. Okay, what we get is x plus epsilon v2g plus minus 1 plus epsilon v2b plus 2x plus epsilon v1g. And what else? Plus minus 2 plus epsilon v1b plus x v0g plus minus 1 v0b. Okay, and this is further simplified to x, so we have the x terms and their coefficients are v2g plus v2v1g plus v0g. Okay, good. All those, we notice that all those have the state as g, so together we notice that this is just a prior of that, which is 1/2, and plus -1 v2b plus v1b plus v0b, and again this is 1/2 to the prior, and plus the epsilon terms. Okay, so this one actually doesn't matter because epsilon is pretty close to 0. So it has some b's, has some g's. Okay, we just write those together. Okay, so this is pretty close to 0. Okay, so finally it looks like, okay, so this is pretty close to 1/2 x minus 1, right? So because we assume that x is a number less than 1, so this is a negative number. Okay, so this is a negative number, then it means that the inequality number 1 implies number 2. Okay, so the reason is that because the left hand side of 1 is less than the left hand side of 2. Okay, so since the left hand side of 1 is a smaller number, and if that is already something that is a positive term, then it means that the left hand side of 2 is also positive. Okay, then the 2 is automatically satisfied. So then we can just ignore the number 2 and we just focus on number 1 here. Okay, so that's a pretty important simplification from this step. And we observed that we previously in the other example, in the judge and prosecutor example, we also sort of removed the other constraint, right? So that's something we can further think about. Okay, So let's move on. So now we can start to solve this linear programming problem. So let's rewrite that to make it clean. Max, so to choose v's, 2v 2g plus 2v 2b plus 2 v 1g plus 2 v 1b. So that's the objective. Subject to now this becomes pretty straightforward, right? So the first is that v2g plus 2v1g plus v0g is the half. So those are the consistency requirements. Just copy and paste. Okay. And the next thing is that the first inequality, right? So because the second one is implied by the first, so we just copy and paste the first one, and minus 1 plus epsilon v2b plus x v1g plus minus 1 v1b is a non-negative number, okay, by the obedience requirement. And we copy and paste all those requirements for the outcomes to be non-negative numbers. Okay. So now we can take a look at those things here, those constraints, and we can further simplify this, or we can have some pretty simple intuition from this. So actually, from those inequalities, we can observe that we should have this to be 0, this v0g to be 0, this to be 0 as well, v1g, and we should have this v2g to be 1/2, to be exactly this number here. The reason is that we notice that we don't have v0g in this inequality here, okay, in this constraint. So that's the first part. The second part is that although we have both v2g and v1g in this inequality right here, okay, but we notice that those two terms, this is sort of like v1g has a bigger cost, okay, so we need 2 times v1g to enter this constraint here. So namely, we can just allocate those sort of like the resources to all those resources to v2g to be equal to 1/2, because those v2g and v1g, they're sort of like the same coefficient here, right? So if we put all those resources and we allocate all those numbers toward the v2g, then because they have sort of the similar, this epsilon is pretty small number, so those two have this pretty same coefficient, then if we have a larger v2g, then this should yield a higher utility for us as the solution, right? So that's the intuition here, okay? Pretty simple and useful intuition for us to further simplify this problem, okay? So then namely, then it's optimal to let v0g to be 0, okay, and also v1g to be 0 and v2g to be 1/2. And then from this, then this is pretty quickly simplified, right? Okay, so now we can rewrite this problem again and further simplify that. So max by choosing v, then this becomes very simple. So this is just v2b plus 2v1b, right? Because the other terms there is just either constant, right? So 2 times this is 1, but we don't need to write constant in the object function because it doesn't matter when we are maximizing, and those zeros just disappear, okay? So our objective function is further simplified and subject to the consistency, it's 1/2, okay? And the inequality for the obedience, 1/2 x plus epsilon plus minus 1 epsilon v2b plus minus 1 v1b is a non-negative number. This is just inequality. And v0b, v1b, v2b, we has to have those things here, okay? That is related to what we have above, okay? And the other terms we just throw them away. We don't need them anymore. Okay, so and actually this one, right? Because we have this v0b as a non-negative number, then we can actually write this as v2b plus 2v1b is less than or equal to 1/2. Okay, then this is further simplification. Okay, so altogether, perhaps we can just rewrite it again. So it's maximize by choosing the v's, 2v2b plus 2v1b, and subject to v2b is less than 1/2 minus 2v1b, okay, from this above, and then the inequality. Okay, so we can rearrange those terms and they become this, okay? And of course, v1b, v2b are non-negative numbers, okay? And from here, we can just divide that coefficient for the v2b to the other side. So this v2b is less than or equal to, because we are dividing a negative number, so the inequality sign has to be reversed. So this is x plus epsilon over 2 times 1 minus epsilon minus 1 over 1 minus epsilon v1b, okay? So now we are pretty close to the final result or the graph part, okay? So now I think we're good to go and start to plot those pictures and solve this new programming problem. Okay,